Okay, yeah, thank you for the introduction. Okay, so this I'm going to talk about Monte Carlo rendering of strongly forward scattering media. And this is commonly found in the real world as fog or water. And sampling paths in these media can be quite difficult, especially if they are dense. So, for example, in this scene, we have a cloud and some golden statue that's embedded inside of it. And if you just use path tracing for it, this is still very noisy, even at high sample counts. So our sampling can improve on that a bit, but it can be a bit hard to see here. It's a bit subtle because in this render, our method only affects the multiple scattering component. So you can see that a bit better if we just focus on the right side, where the multiple scattering is more dominant. And I'll go back to path tracing again, and back to our sampling. So as I said, we are going to sample paths for Monte Carlo integration of the measurement contribution function. And the classical approach here is to do just path tracing from the camera. And it's basically doing what a photon would do in reverse. So we sample the free flight distance, which is on average one mean-free path, and then sample a phase function for the next direction. And because we are we are so strongly forward scattering here, it will continue almost in the same direction as before. We can continue extending paths this way, but we are unlikely to ever hit the light source, of course. So we're doing next event estimation and explicitly connect to the light source. However, the direct connection misses important light paths like these, where the light scatters around multiple times. And this is quite likely here because of the density of the medium. And also photons are likely to continue in this straight line because of the forward scattering. So these multiple scattering paths are very significant here. And in this project, we are going to sample such a path as a connection path, and we will call this a bridge path. So you may ask why we need to sample these paths explicitly anyway. Can't we just approximate that with some multiple scattering approximation because it will diffuse? And this is actually not the case here because, as I said, the photons travel on almost straight paths. So if we look along that shadow edge, it stays sharp after even a few bounces. And only if we go to really long paths, there's no difference anymore between what's in shadow and what's outside of shadow. So for the medium scattering, yeah, as I said, for this part, we might be able to use some diffusion approximation. But for the part for the left side, where this medium order scattering happens, the visibility is actually quite important, and we need to do explicit path sampling so we are able to test for visibility against the geometry in the scene. So let's turn back on how to actually sample those paths. And this can be challenging even if we just consider single scattering, because of the phase function, as I said, it's very narrow and it just allows for a narrow range of directions. So it's almost specular transport here. And then there's also the geometry terms, which have this reciprocal squared distance that can lead to infinite variance if we don't importance sample it. Luckily, there's a paper that does exactly sample this, which is called Once More Scattered Next Event Estimation, and it was presented at this conference 2 years ago. It roughly works like this. So they sample the phase function first, actually. Then they derive a circle where each point on the upper arc of this circle maintains this angle with the two vertices that we wanted to connect over the third additional vertex. And then we can just pick a point on this arc, and it will give us a valid configuration. So we can just do a bit of math and derive all the necessary equations for that through change of variables. And then we will see that this actually cancels the geometry terms and achieves what I've said before, but it's not so easy to generalize this to more than one bounce. There's other works that target the multiple scattering more explicitly. For example, the one by Georgiev and colleagues, which is about double scattering. And there's also and they do condition, like they tabulate the conditional densities on the way, but as I said, it only works for up to double scattering. And there's multiple vertex next event estimation by Weber and colleagues. This works for any number of vertices, but it doesn't account for the correlation between all the vertices. So it will, it won't work as well for longer paths as we will see later on. And both of these works also suffer from approximating the phase function. So our goals here is to support any vertex count. So we want to handle the general case here. We also want to do explicit sampling of the phase function, so we don't get any approximation errors, and because this is generally available in renderers already. And we also want to sample the geometry terms, so we don't get this infinite variance. So if you look at this list of goals and turn back to simple path tracing, we might think like, doesn't this already solve all the problems? Because we can trace like any number of vertices, we get any number, like arbitrary long paths. We can also sample the phase functions along the way. And we can also sample the geometry, like this geometry terms are implicitly sampled here because we are in the solid angle domain. So the only issue here is really that we just arrive at some random other point that we didn't want to go in the first place. So our key idea here is to maybe just fix that fact about it, like transform the path in a way where it will preserve all the important sampling properties of the path, but end up at the point that we want to connect to. So we do this by first rotating the path around the starting vertex and then scale it to match the distance between the starting vertex and the light source vertex. Because we did constant uniform scaling here, it preserves all the angles. This keeps the phase function sampling intact. It keeps all the geometry terms intact up to scaling. And actually, this already solves our goals. So this simple transform already is our sampling method. And we use this to connect to the light source, and this we will call this a bridge path. And we will call the path that we sampled using path tracing the preliminary path before we transformed it. So now the only thing left to do is to derive the probability density function to put this into Monte Carlo renderer. And for the preliminary path, this is quite easy because it's just the product of whatever we sampled before. It's the product of the phase functions, the free flight distances, and the geometry terms. But we don't know how to get to the bridge path PDF yet, but because there's no bijection, there's multiple paths that transform to this bridge path. So we can't go both ways, we can go only one way. And therefore we can't just apply change of variables and directly at least. This is because the final vertex will always be the same because we explicitly derive the transformation in a way that it will be the same. So therefore, we will have a different dimensionality between the two probability densities. So as I said, because there's a different dimensionality, we can't use change of variables. However, we can fix it by just making up some bijection. And we do it in this way that we just remember where we came from. So during the transformation, we will remember the last vertex on the preliminary path. So this allows us to go back and forth between a preliminary path and that bridge path again. So we can use a Jacobian to at least transform the densities between these two spaces. But as we don't want this extra vertex, so we have to integrate it away in the second step. So we have to compute the marginal density of this probability density of the bridge path and that extra vertex. So we can expand that integral a bit by using the Jacobian, as I said before. Then we have everything ready and just need to compute the integral because this is just a product of the Jacobian that can be derived in a simple way because it's just the scaling and the preliminary path PDF that I've shown before. There's one more trick that we can apply to simplify this a bit, and this is because the rotation that we did to match the paths will actually make it doesn't really matter where we started from. So we can start from any direction as the first direction. So we're just going to fix this. And if we choose the same direction for any of the preliminary paths here, the end vertices will align. And yeah, this will just be a single, they will all just be on a single line, and we can integrate along that line. So the integration just changed to a 1D integral, and we are just integrating over basically the scaling of this preliminary path. So we can expand this further, and I don't want to go too much into detail and just show the relevant details here, which are mostly just the free flight sampling PDFs, which makes it possible to solve this in the first place. And yeah, it's just an integral of exponentials here. And the only trick we need to apply is to move the product of all the exponentials inside. So it's exponential of a sum. And then this is quite straightforward to solve. And we just end up with this equation. And then this is like, we can put this in the PDF. There's some more terms missing here, but this is like, for example, the phase function PDFs and so on. But this is straightforward to multiply to. So now let's just look at some results. I'll show it on a simple test case scene where we have a point light source in the middle. And this is all embedded in an infinite homogeneous medium. We'll compare against equiangular sampling, the multiple vertex NEE, once more scattered next event estimation, yeah, and ours, of course. So I'll show the root mean squared errors in the corners. And yeah, if we just go to single scattering and like moderate forward scattering, all of them still do relatively well. Even though equiangular does not sample the phase function here, it's not so important to do so, and it is slightly worse, but not much than the others. And this changes once we go more forward scattering. So here, the equiangular clearly becomes worse. And once we go like even more forward scattering, then also the multiple vertex NEE starts to get worse because it approximates the phase function. And ours and Omni can remain constantly good. And this is to be expected because Omni was designed to handle especially this case. So let's look at something more interesting, or what we wanted to achieve here, which is multiple scattering. So I'll show a strongly forward scattering phase function and increasing path lengths. So this is path length 3, which I've shown before, and there's everything as you've seen before. But already at like 1 ounce more, both Omni and the multiple vertex NEE get worse. And for Omni, this is because we have to now trace a prefix path, so we actually achieve the whole path length because it will only handle the single scattering component. For multiple vertex NEE, this is just because it perturbs all the vertices independently, so we don't have any correlation between the vertices, and this will just break for longer paths. And this gets only worse if we look at like even more bounces, while ours can roughly maintain its sampling quality throughout all the different path lengths. So we also tried this for very long paths, like shown here, for 20 to up to 100 vertices. And as you can see, like eventually you can of course see that it gets worse with more vertices, but it's still much better than path tracing, which basically is not able to render this at all here. Okay, so our sampling worked well when we just looked at the fixed path length, but when we're making a connection, we actually need to decide upfront like how many vertices we would like to have in between both vertices, like the start and the end vertex. So what we want to achieve here is to match the edge length of that bridge path to the mean free path on average, because the expected number of collisions is the optical thickness, which is like the track length or the distance we travel inside of the medium divided by the mean free paths. So along the straight line connection, this is just the distance between the start and the end vertex, the track length, I mean. And we can just use free flight sampling to sample this, and this is what multiple vertex next event estimation and also delta tracking do. Since this is a Poisson process, the number of collisions also follows a Poisson distribution with the optical thickness as a parameter. which, as I said, is the track length divided by mean free path, or as it's written here, multiplied by the extinction coefficient. And we could use that, but our case is actually a little bit different because our track length will be longer than just the direct connection. And we will take a slight detour, which depends on like how far the sample directions go away from the straight connection, and also on how many vertices we sampled. So this is actually a problem because this is some cyclic dependency. We wanted to sample a vertex count in the first place. So what we do instead is to think of the full estimator here, which combines every path length as the sum of individual estimators. So each estimator handles only one of the path lengths. And we can, like, choosing one of the estimators is the same as choosing a path length. And we can optimally choose such an estimator in proportion to the square root of its second moment, which of course we don't know in advance. So what we do instead is to do some pre-computation. We run our estimators in a homogeneous medium and pre-compute the second moment. And we also need to do a second simplification, which is to assume that we don't know the exact directions, but we just know the parameters of the phase function that will lead to sampling these directions. So in a way, this is a dimensionality reduction. So for each combination of the vertex count and phase function parameters, we will have a 1D function of optical thickness, like shown here on the right, which we approximate using a spline. And then during path sampling, we can recover the distribution from that. Here we compare different methods of sampling the path length. One is the Poisson in two different versions, one with a scaled optical thickness, and our method both with first and second moment. So if we just look at path lengths that are limited to 10 here, they all roughly look the same, I would say. But if we go to longer paths, there's actually some outliers that appear, which is due to the Poisson sampling missing some long paths that still have a high contribution. So these are undersampled, but our second moment-based sampling can cover these longer paths as well. So there's a bit more in the paper. We also talk about how to put this into renderer, and we show some more results with some geometry in them, not just point light sources. And we also show a second method to do the distance sampling, which we call the constraint-based sampling. We also show that this is actually equivalent to Omni for the single scattering case, but it only works for single and double scattering. And actually, we haven't seen any practical benefits from using it. So we just use the scaling-based method, and the other one might still be of theoretical interest to you. So in conclusion, we showed how to sample a connecting subpath between two vertices in a medium. We can use any vertex count for this path, and we sampled all the phase functions and geometry terms on the way. Also, this whole construction turned out to be quite simple, which I like. So for future work, I think it might be interesting to reconsider that problem of sampling the vertex count, because I think there could be a more elegant solution to this problem here, but yeah, we had to do something. So I guess it might be interesting to look at that again. Also, it might be interesting to put this inside of bidirectional path tracing, where you could not just connect to light sources, but you could make arbitrary connections between subpaths, which might be interesting to generalize this to cases where the light source is not embedded inside the medium, as in the examples I've shown before. Thank you for your attention.